Spontaneous or product-favored processes. A reaction is said to be spontaneous if it occurs without any continuous outside intervention. This is a key word here. For example, if you just add a quick shot of energy and then stop, that can still be considered spontaneous. However, it does not mean fast. Typically, if you hear something is spontaneous in normal conversation, you think it's going on fast, but that doesn't work for chemistry. Many spontaneous reactions are kinetically slow. In other words, they move slowly, but they do happen without any continuous outside intervention. And that's because of an activation energy barrier. We'll talk about that later in the kinetic units, but you can imagine if you have some reactants over here and you want to form the products here, you should be able to do that because the products have less energy, but to get there, you have to put an initial shot to get over that curve there, and that's called the activation energy. The reaction itself favors the formation of the products. Why? They're more stable, and that ties directly into lower energy. However, it is kinetically slow because to get to this lower energy, you first have to put in a big shot of energy to get over that curve and get down there. A better word for spontaneous is product favored. This means that products predominate over reactants in a reaction. And another way of saying that is there are more products than reactants after the reaction is over. Another term that means the same thing is thermodynamically favorable. An example of a process, but it's not a reaction, that is thermodynamically favorable is heat flow from a hot object to a cooler object. It does not go the other way. Conversely, non-spontaneous reactions are reactant favored. In this case, reactants predominate over products in these reactions. There are more reactants than products after the reaction is over. So we've basically just inverted the definition. Another term that means the same thing is thermodynamically unfavorable. An example of a process, again, this is not a chemical reaction, that is thermodynamically unfavorable is heat flow from a cool object to a hot object. It just doesn't go that way. We've now split the reactions into two types, product favored and reactant favored. And what we're going to do now is take product favored reactions and split that into three types. Okay, so we had the product over here, we had the reactant favored, and we're going to have 1, 2, 3 types of product flavor. First is potassium metal plus water, yielding potassium hydroxide and hydrogen gas. This reaction happens immediately on contact of potassium metal with water. It is so exothermic that the hydrogen gas produced here ignites. So this is a very dangerous thing to do. A lot of chemistry teachers will do this under very controlled conditions to keep everybody safe. They'll drop a little bit of potassium in water and you get the reaction you see over here. It's a bit of an explosion and fire and gas. So this is not something you do on your own. During the early development of thermodynamics, scientists thought that exothermic reactions were always spontaneous. We'll learn that the exothermic nature is important, but it is just part of the explanation. Here's type 2. Steel, which is an iron-carbon alloy, will rust on exposure to oxygen and forming iron oxide. This is a very, very slow process, but eventually, for example, the Golden Gate Bridge, that's right down here, which is built of steel, would be converted to iron oxide and would crumble. So the bridge needs regular painting to protect it from this corrosion. And here's just a little sidelight here. Rusting is the formation of iron oxide. This is an example of a thermodynamically favorable or spontaneous reaction that is kinetically slow. It takes a long time. And here's our third case, reaction type 3, and the example is burning natural gas or methane. So here's methane plus oxygen yields carbon dioxide and water. You can mix methane and oxygen and absolutely nothing happens. However, if you just have one spark, one little input of energy, for example activating the ignition switch on a stove, the reaction will go completely to products. The spark provides the energy necessary to overcome the activation energy barrier for the reaction. Remember a few slides ago we started with the reactants here, and this is an energy diagram. We put in that energy, that excess energy, which in this case comes from the spark, gets the reaction going, and then at the end your products have a much lower energy. They're more stable. Right here, that's the spark on your stove. So if you can classify product-favored reactions into three types, you can do the same thing with reactant. You just have the reaction going in the other direction. It's the exact opposite. So here's the three examples we have. We have potassium hydroxide and hydrogen making potassium and water. You have rust turning into iron. And you have carbon dioxide and water turning into methane. Notice the X's here. These guys just don't happen without a continuous outside intervention. And frankly, I'm not sure how you do this, how you convert rust back to iron. You probably have to put more energy into that than you would get from just taking iron out of the ground. So the key here, continuous outside intervention to make it happen. If you do not have that continuous outside intervention, none of these reactions go the way they're listed. Let's talk about the continuous outside intervention a little more. It means that you have some flow of energy, a continuous flow of energy required for the products to form. This could mean heating a reaction, or it can mean doing work on the reaction. Well, what does it mean doing work? Well, when you compress a gas, that's a good example of doing work on a system or a reaction. Again, we've said this several times, but let's remember, a spark is not a continuous outside intervention. All the spark does is provide energy to overcome that initial activation energy barrier. Let's draw that curve again. This is a pretty cool curve. This is energy on the y-axis, and this would be time over here. Once you get over this curve, then you have a self-sustaining reaction, and it will keep going until it's finished. Processes that are favorable at one temperature may not be favorable at other temperatures. Let's take an example. We're going to melt ice to form water, and then the opposite. We will freeze water to make ice. If your temperature is greater than 0 degrees Celsius, melting ice is product favored. Okay, so you go from the ice over to the water. However, if you are less than 0 degrees Celsius, forming ice is product favored, so it depends on the temperature. A fundamental driving force for product favored reactions is an increase in a thermodynamic property called entropy. This is really cool, and we're going to define that all kinds of ways because it's a little bit tricky, a little bit trickier than energy. And there's no simple definition of it. But let's start by looking at it as a dispersal of energy. You have energy spreading out. A process that is product favored is one in which energy spreads out or disperses. Another word for this is disorder. So the greater disorder, the greater entropy. For example, if your room is very neat and then you go through a whole day and you're doing work in there, you have friends over, you've got books all over the place, it's a total mess, you have increased the entropy of your room. Now let's look at a more chemistry or physical example of this. We're going to worry about heat transfer from a hot object. So if you take a hot pan on a stove and you let it cool to room temperature, initially all the thermal energy is concentrated in the pan, on the pan. Following the cooling, the energy has been dispersed over the pan, the stove it is in contact with, and the surrounding air. It's been spread out. The energy has all moved away, a lot of the energy has moved away from the hot pan. So you have a dispersal of energy over a greater number of particles, right? The particles in the pan, the particles in the stove, the particles in the air, and it is thermodynamically favored. It will not go the other way. Let's look at it now from a math point of view, a probability point of view. Dispersal of energy occurs because it is much less probable to have energy concentrated on a few particles, and more probable to have it spread out over many particles. So let's take 3 particles, A, B, and C, and 3 units of energy, and this here is a unit of energy. Which of the following arrangements is more probable? Does A get all the energy? Does A get 2 units, B gets 1, and C gets none? Or, I'm kind of giving a hint by putting a box around it, does each particle get 1 unit of energy? And let's see what our answer is. Well, 3. You kind of guessed that because I put the box around it. The energy spreads out as far as it can go to all the different particles, which in this case, there's 3 of them. When particles in a condensed state, and what do I mean by that? Well, a solid, expand to occupy a bigger volume, there is a dispersal of energy and therefore an increase in entropy. A liquid changing to a gas seems obvious because energy will accompany the particles as they disperse, as they spread around. You can see them over here. Also, when the gas molecules disperse, they have more energy levels than in the condensed state. You'll just have to believe that for now. So there are more ways to disperse energy as the gas molecules spread out. Here's a question. Is the expansion of a gas thermodynamically favorable? Let's put bromine gas in flask B here, and you have a little valve here that's shut. I have another globe here that's a vacuum. There's nothing in there. You open the valve right here. See how it's open now? Bromine gas will spontaneously move from flask B to flask A. The gas will keep moving until it is equally distributed between the flasks. And when we had the states of matter chapter, we know that gases will expand to fill a container, no matter what shape it is. So that's why it's going from B through the little valve into A. From a thermodynamic perspective, it is more probable for gas to expand and fill an entire container because now the energy is dispersed. It's not just over here, and it's not just over here, and it's not just a little piece here. It'll spread out as far apart as it can get, so it'll fill both containers. Expansion of a gas is thermodynamically favorable. How about compression? Well, you're probably guessing no, and you'd be right. So what we have here is we have both flasks filled with gas, and we want to know, is it possible at some point, if we just let it sit there, for all the gas over here to flow into here, and then leave A in a vacuum, and all the gases there in B? Well, no, that's highly improbable. It's an example of a process that can only be reversed by doing work on the system. So what we would have to do is put some kind of plunger in here and push all the gas into B and not let it come back. So you're doing work on the system, so that is not thermodynamically favorable. Identify each of the following processes as product or reactant favored. Write an equation if necessary to identify reactants and products. So what I'd like you to do here is, before you pull out the answer tab, next to each one of these numbers here, put either RF for reactant favored or PF for product favored. So take some time to do that now, and when you're ready, pull out the answer tab. Okay, so let's pull out the answer tab, get rid of that, and let's talk about these guys. So another name for product favored is thermodynamically favorable, so it will happen without any continuous intervention or addition of energy. So let's go through these. Water boils at temperatures greater than 100 Celsius. Yes, it will do that, so that's product favored. See the PF over there? Heat flows from a hot object to a cold object. Yes, thermodynamically favorable. That's product favored. However, carbon dioxide and water do not form wood. Yeah, you just can't mix some carbon dioxide and water and come up with wood, right? It goes the other way. So that would be reactant favored. And you can see the 3 there is reactant favored. Ice at 1 degree Celsius melts. Yep, product favored. Salt dissolves in water at 25 degrees Celsius. Yes, product favored. A rusty car does not become rust-free. That's correct, right? You're not going to have the rust all of a sudden turn into iron and oxygen. It just doesn't happen. So that's going to be reactant favored. Ice doesn't melt at minus 10 degrees Celsius. It stays ice. Reactant favored. And gas fills a container uniformly. Yep, thermodynamically favorable. Entropy increases, all good. So that is product favored. And if you had a little trouble with these, please go back and review like the last dozen or so slides. Let's summarize all of this, because a lot of new concepts going on here. For any chemical or physical change, and physical change would be things where heat moves from one object to another, reactants have energy concentrated in a very few particles or energy levels, and in which products have energy spread over many particles or energy levels. If that's the case, your reaction is product favored. So your reactants over here, everything's concentrated in a small spot, okay? And then if your products, the energy is all over the place, it's been dispersed, then that is a product favored reaction. That shows us why fossil fuels such as coal, natural gas, and petroleum are so incredibly valuable. In nature, there's a low probability that energy will be concentrated over a few particles, just like there's probably a very low probability that your rooms will always be neat and everything orderly and put in its right place. However, for energy sources, this is just the case. You have a whole bunch of energy concentrated in very small areas with the coal and natural gas and petroleum. These fossil fuels are a valuable source of chemical potential energy. However, we keep using them, and it's hard for us to make more of them, right? It took millions of years for that stuff to be made, so they have to be conserved.